continuing with our anti-differentiation problems here. Number 9. We look to expand, or we try to expand, but it looks like this is not going to be a good fit. The denominator has too many terms. U substitution is not going to quite work either. If we let the u value be what's in the denominator, the derivative is going to produce an x or two x's or x, and that's not going to match with what we have up in the numerator. But it does fulfill the condition where the degree, the variable in the denominator is 2 degrees higher than that of the numerator. So it looks like we can attempt to match with arc-trig and arctangent specifically because we don't see a square root. So it looks like arctangent could be a good fit. But we have to complete the square to get our parentheses to show up, and so that we can find our u value and our a value. So to complete the square, we're going to try and create a situation where we can get a trinomial to factor nicely. So x squared plus 2x plus space plus 2 minus space. So we're trying to figure out what will cause these three to factor nicely. And what's going to cause it to factor nicely is filling the blanks with b over 2 squared. Our b is 2, so 2 over 2, that's b value. 2 over 2 is 1, 1 squared is 1, so we do plus 1 and minus 1 to maintain balance of our original expression. The x squared plus 2x plus 1 factors out to be x plus 1 times x plus 1, which is x plus 1 quantity squared. And then the 2 minus 1 becomes 1, so that just becomes 1. If I can rewrite that in a better form, I can rewrite it as parentheses squared plus 1 squared. That makes it easier for us to identify our u value being the x plus 1. Remember that the u value is always has the variable in it, and the a value is always just the constant. So u value is x plus 1, our a value is 1. This matches, we find the derivative, du over dx is equal to 1. So dx equals to u, we make our substitutions, and we get everything in terms of this form. Dx gets replaced with du, x plus 1 gets replaced with u, 1 gets replaced with a squared. So now we can follow the rule here. 1 over a, which is 1 over 1, arctangent of u over a, so x plus 1 over 1 plus c. Okay. Answer choice C. All right, number 10. All right, number 10. Notice that we always want to try to expand first. There's only one term in the denominators, and the numerator has a degree that is manageable in terms of expansion. So we're going to bring that square root of up to the top, and we're going to expand using power rule. But something we've got to be careful about, the 4 is not going to come up with the square root of y. We're going to push that 4 out as 1/4, and that will kind of help separate the parts that we don't have to worry about until the end, and we can kind of just worry about the parentheses and the square root of y. So when that square root of y comes up, we can rewrite it as y to the negative 1/2. I'm going to separate that 1/4 away from my expression. I do want to apply power rule to each of these terms, but I need to get rid of the parentheses. I have to expand out my binomial. So expand this out. We get 4 minus 4y plus y squared. Distribute it through the y to the negative 1/2. I'm going to add exponents. So y to the first power and y to the negative 1/2. 1 minus 1/2 is 1/2. 2 minus 1/2 is going to be 3/2. And looks like everything is set up and ready for power rule. Okay, so here's power rule. We add 1 to the exponent, so this becomes y to the 3/2. Or sorry, to the 1/2. Negative 1/2 plus 1 is 1/2. 1/2 over 1/2. The 1/2, we add 1, we get 3/2 over 3/2. 3/2, we add 1, we get plus 2 over 2, so 5/2 over 5/2. And all the meanwhile, I have to keep track of the fact that there's still coefficients in front of 2 of these terms, and then I have to worry about distributing that 1/4 through eventually to all the terms. So if I clean all this up, flip the 1/2 as 2, flip the 3/2 as 2/3, flip the 5/2 as 2/5, distribute the 1/4 through, and we end up with 2y to the 1/2 minus 2/3 y to the 3/2 plus 1/10 y to the 5/2 plus c, and that's answer choice D. All right, number 11, we look to expand first. Too many terms in the denominator, so it looks like we can't do that. U substitution, well, if we let our u value be 1 plus e to the 2x, the derivative for e to the 2x would be 2e to the 2x, and that is not going to quite match the form of my numerator. So maybe it's arctangent rule. So if I can get my denominator to be parentheses squared, we know if it's arctrig, it has to be arctangent because we don't see square roots in the denominator. If I can force those two terms to be parentheses squared, then what's inside the parentheses will be our a and our u value. So the 1 can just be rewritten as 1 squared. E to the 2x can be written as e to the x quantity squared. A value is 1. Our u value is e to the x. And we go from there. U equals e to the x. Derivative is going to be e to the x. dx equals du over e to the x. We make our substitutions in terms of a and u. The e to the x will cancel out nicely. And this matches perfectly with our arctangent rule. So arctangent says 1 over a. So our a value is 1 over 1. Arctangent of u over a. So e to the x over 1 plus c. So represent our answer either as arctangent or as inverse tangent, and the answer choice is using inverse tangent, so answer choice A. All right, number 12, we still want to apply our antiderivative priority steps, but these are definite integrals, so that means after we find our indefinite integral, we're going to have to work in those bounds and provide a numeric solution. So first thing, expansion. Is expansion possible? Too many terms in the denominator, that's not going to work out. U substitution. We can't identify a u value that will match the other side, so not U substitution. But it looks like this could fit nicely with our condition for long division or synthetic division, which is that the degree in the numerator, the variable degree in the numerator is greater than, or at least the same or greater than the degree in the denominator, and that is the case. So we can apply either long division or synthetic. I'm going to show using long division just because long division can be applied for more situations than synthetic. Synthetic is potentially faster, but it's also more restrictive. But long division can work in this situation. So long division, x plus 1, you got the square root divided by, or divided into the x squared plus 6x plus 6. We ask ourselves, x times what gives us x squared? And it's going to be x. So we take the x, distribute it through the binomial. So x times x is x squared, 1 times x is x. We draw our line, we change our signs, bring down our terms. 6x minus 1x is 5x, 5x plus 6. We go back to the top. X times what gives us 5x? X times 5. So we bring that 5x down, multiply, distribute it through. 5x is 5x, 5 times 1 is 5. We draw our line, we change our signs. The 5x cancels out. 6 minus 5 is 1. We can't go any further. X can't go into 1, so we call this the remainder, 1 over x plus 1. We haven't found the answer. We've just created a form so that our antiderivative will be easier to, the rules are easier to find. So now if we go back to our integral problem here, this is a rewrite of our integral problem. The x and the 5 are easy to identify. We can apply power rules separately for these terms. And 1 over x plus 1 is a u substitution problem that will eventually turn into a natural log problem. So we let our u value be x plus 1. Derivative is du equals dx. We get this in terms of u, so 1 over u du. This matches nicely with our natural log rule. So natural log absolute value of x plus 1. So there's our antiderivative. X becomes x squared over 2, 5 becomes 5x, and we have the natural log of absolute value of x plus 1. Now we look at the beginning of this problem. It's dealing with bounds, so now we work in the bounds. Okay? And the way we work in the bounds is we always plug in the top value first. So the top bound gets plugged in for each of the variables. So we get 2 squared over 2, 5 times 2, natural log of absolute value of 2 plus 1. Then we do minus big parentheses, and then plug in the lower bound. Okay, make sure you have a set of parentheses here, so we remember that this minus is going to distribute to everything that follows after. So 1 goes in for x, we get 1/2. 1 goes in for 5x, we get 5 times 1. Natural log of 1 plus 1 is 2. And now we have a bunch of terms that we can just try to clean up. So we get 4 over 2 is 2, plus 10 is 12. Natural log of 3. 1/2 plus 5 is 5.5 with a negative in front, so minus 5.5 minus natural log of 2. Combine some more like terms there. 12 minus 5.5 is 6.5. Natural log of 3 minus natural log of 2 is the same thing as natural log of a over b, so I can rewrite it as natural log of 3 over 2. So that matches answer choice C.